We can't edit it out. We can't beep it out, so be careful what you say.
Oh. Okay. So yeah, my name is Elijah Flinner. I will be around most of the afternoon. So as you're working on stuff, you want to ask me questions. My office is C127. There's other cubicles in there too. But you can come in and find me. There's someone in there. You can ask if the door's locked. There's no one there. And once again, I am fairly tired. All right. So we will start. I'll start today. I'm going to describe, the idea is I'm going to go through some molecular dynamic simulation. I'll describe how this is done and show you some examples of specifically a step-by-step procedure of the what's generally done to do a molecular dynamic simulation. Then I'll describe to you some analysis that's very typical in molecular dynamic simulations, and the MD analysis tool, which is a Python programming, since you have been learning Python programming, which is a Python programming toolkit that help you do the analysis. And then when we're done, I have a bunch of example files, and I'll tell you what each one of these files are doing. And then this afternoon, what you'll do is you'll go through the example files, and you can run on the cluster all the examples. You can run the simulation, equilibrate, do benzene, since you guys have been doing a lot of work with benzene. Equilibrate the benzene, write some Python scripts to do the analysis, and do some very typical analysis of molecular dynamic simulation in condensed phase. So, first of all, what is a classical molecular dynamics simulation? I am not going to be talking about any quantum mechanics simulations, so this is just classical mechanics. And really, it's a numerical method that's based on Newton's equations of motion in general. You don't always solve Newton's equations of motion, but this is the beginning of the method. It's used to calculate thermodynamic quantities most of the time. For example, you calculate specific heats, compressibility. These can be used to, with free energy differences, diffusion coefficients. It can be used to test theory. It can be used to understand how the molecular motions of the individual atoms and molecules are related to the what is measured in experiments. Experiments cannot, experiments in general do not follow the motion of individual molecules. So you can use the information from these to learn how the molecules influences the experimental result, how those positions in motion interact. So it provides a means to connect the microscopic AV items with the experimental results. So what are you doing? I believe yesterday you talked about force fields a little bit.
We almost did.
We almost did. Okay. So I was under the assumption that that was going to happen. So I didn't have much on force fields. So what is from something like what you were learning earlier on, and there's other ways to do this. People come up with empirical forms of force fields, and these are potentials. It describes most of the time conservative forces for the atomic motions. Okay. If you remember physics, you can get the forces from a potential by the derivative of the atomic position. I don't know if there's a pointer. No? Anyhow, I can point. So this is what this is saying. The forces on a particle equals negative gradient of the potential. And that is the force on the particle. So the force fields are these potentials. And later on, we'll be using the fact that when the potential is on a mineral, the force is zero. Because you guys didn't talk about this. Let me just show you a quick example of a very typical, is this, I don't know. It's not very good, but it works. So this is an example of a potential. This is the Leonard-Jones potential. This is actually a paper comparing all these force fields for benzene. So different molecules, for the same molecule, you can have different force fields. People do studies where they compare different force fields, and they compare them to different experiments and stuff. And so that's what this paper is doing. And so this would be a potential. Is Rij is the distance between particles I and j. And this is Leonard-Jones potential, and this is the cool part. So this is going to be electromagnetic interactions. So the Q is charged on particles, and this Rij will be the distance between the particles. So all the particles will interact with this. There's bonding interactions, there's different interactions, which I don't have much prepared for because I thought you guys were going to talk about it. But so people come up with these force fields using quantum mechanical calculations as well as using experimental results. And they tweak the parameters, the epsilon Leonard-Jones field, so we see those parameters to recreate experimental results. So then for molecular dynamics, you use Newton's laws. It's force equals mass times acceleration in terms of acceleration. The force is coming from what's potential. And the basic steps are then use those accelerations to the velocities. You use the velocities of the positions, the forces of the new positions, and you can do there's many different numerical routines that you can use. But this is the general idea behind it. And what you do in molecular dynamics is you calculate quantitative interest on the positions and the velocities. And many people think of this as some sort of numerical experiment. The reason we do this is that we can't sit down and solve equations for all these atoms in a practical problem. And so, but we can numerically do it in computers, and so it's some sort of numerical experiment. One of the important things that I'll be talking about a little later is if we solve Newton's equations of motion, and we use conservative forces, then the total energy, kinetic, which is 1/2 mv squared, and plus potential. So this is conservative. We use this kinetic energy a lot of times in the simulations, and I'll mention later to define the temperature. And then to control the temperature. All right. So the first thing, there are several steps you have to go through. First step is set up the simulation. Then you have to, sometimes you have to equilibrate it. Most of the time you have to do some equilibration for the simulation. And then you got to run a production run to calculate your quantity of interest. So first of all, to start setting up a simulation, you start with some initial conditions. The initial positions, these can come different. You create these different ways. I think you created, first day you created a whole bunch of benzene molecules, right? And so that'd be one way to create the initial positions of the atoms. A lot of people use periodic structures because then you know that there's not a whole bunch of overlap. That can cause problems because sometimes the periodic structures just stay there and do not form a liquid for a long period of time. And you don't want that. But sometimes there is no periodic structure. It's not sure with your system. That's an issue. I want to stress complicated systems require some care, but I will show you how to deal with that. Most of the time, the initial velocities are usually chosen from the Boltzmann distribution of velocities. I think we talked about Boltzmann distributions a little bit. But this can be shown that this is the distribution of velocities at a specific temperature. Fortunately, the velocities most of the time will form Boltzmann distribution after a while. So, in setting up the simulation, what's may need to be initially done is to minimize the energy to remove overlaps of particles. Particles are too close. So you get two atoms that are sitting almost on top of each other. The forces are very large. And what happens then is that when you do your numerical integration algorithm, the whole thing blows up. This afternoon, you can take the initial condition that I have in the memorization and try to run a normal simulation, and you can see it blow up. Because the atoms just fly way far away. It ends up not even working because the simulation loses track of what's going on. So most of the time, what people do is that they minimize the energy to remove any of these overlaps. So when you find the energy minimum, remember at a minimum, the derivative of the gradient is 0. So that means the forces are approximately 0. So when it's approximately 0, if you find the minimum, it will be 0. Approximately 0, you can numerically find the minimum, and so it's close to 0. So the initial displacements are due to the velocity because the forces are 0. And so in this way, you can make sure that your simulation doesn't blow up on the start. And then, whenever you're studying, you're probably not going to want it at 0 temperature and whatever pressure minimization is up there. So you want to equilibrate the system to desired temperature and pressure. So we use what's called thermostats to equilibrate the temperature. Many different ways to do this, many different thermostats. I'll describe briefly what our thermostat that today we use, and use what's called a varostat to equilibrate the system with pressure. If you think about this, Newton's equation of motion doesn't have a thermostat, right? So we're actually changing Newton's equation of motion and changing how these particles move when we go through these things. So that's to equilibrate it. And sometimes when you do your sampling, you don't necessarily want to use Newton's equation of motion. And that'll be talked about at some point, for sure. Then you want to run your production run and calculate averages. And it's important to always keep in the back of your mind when you do these production runs that these things is the question you're trying to answer? What are you trying to calculate? Because doing these runs in certain ways, it's important to design it so that you're able to answer your specific question. Sometimes people aren't quite sure what the question is yet, kind of feeling things out, but you really want to be careful with these question runs. All right, the other thing is that so when you, I'm drawing the board a little bit. So when we simulate a liquid, I mean, how many particles are in a liquid? You're going to have over a mole of particles, over 10 to the 23rd particles. You have your coffee or whatever you have there. The computer can't handle that. The computer can't simulate that. So what do we do? What generally done for liquids, this wasn't always the case, but it's generally done, is that you use periodic boundary conditions. And since, oh, I should probably. All right. So what is, oh, I drew this a little too big, right? So what you do is you have so many particles in a simulation box. So here are my atoms. And we'll say that there's n in there. It can be some sort of reasonable number. A lot of simulations I do is like 1,000 particles within our main simulation box. Then you create periodic images of it so that something like that. So you do this in every direction. So that what happens, what you do in the simulation, we'll draw all of them. Is that, say, a particle were to move through the edge of a box. When it moves to the edge, it moves back in on this side. So this is the this way, and this way we can simulate approximately infinite liquids, or very large systems. There's some difficulties in dealing with the periodic boundary conditions. When you think about it, you have this particle on this side. It also interacts with particles on this side of the box, right? If it were to move through, it needs to be interacting with whatever's over on this side. So you have to deal with those interactions. And when you calculate the quantities of interest, you have to be sure to calculate quantities for its periodic image. And that you have to be sure. You can't, what this also means is that you don't want to have a particle interacting with itself. So when you think of those potentials, you're not writing down those potentials as being cut off at some point. But you have to be careful, and most of the time, cut or shift or truncate or change your potential so a particle doesn't interact with itself. So you make the forces go to 0 before that can happen. That means the potential is only go to half a box length. That's the maximum distance. So I'll mention a couple things about how to deal with let's see, how do we do this? These periodic boundary conditions and calculations later. But that's how we can simulate large systems by using only a small amount of molecules. The simulations I have set up have 200 benzene molecules. And so for these simulations, I'm going to use benzene as an example. Since you guys are somewhat familiar with it. It's not the easiest example. So let's take a look at we use Amber to do some of the simulations. So first, let's take a look at the file. So this should be an example of file. And I don't know how practical this is. Samples folder. You need to open DMB. So first, there's, I think they talked about this a little bit. The first thing that VMD needs is a parameter file. So this defines the atoms for you. And so in the example folder, there's this bens.prm top. And then once you load that, hit browse again immediately. You can open up an MDCRD file. So here I have the example set up. I've already memorized the the structure. All right. And so this was the beginning structure that was actually just given to me by Rex. If I remember, somebody pending before this class. There's 2,400 atoms. There's 200 benzene molecules. There's 12 atoms for each benzene molecule. Here, I just ran the minimization. I'll show you. Yes.
When I put in I'm trying to open up the file, like it showed up the black screen. Like, what do you do between like opening up the file and then getting it to show?
Okay, so you'll go back to file. Go down that in the molecule. Go down that in the molecule. Okay. Browse.
Like in the example file.
It should be in the global.
So go to R7 RST file.
MDCRD.
Yep.
MDCRD.
and then I
Oh, no, then you go back to here.
but I hit it
Oh,
twice.
yeah. Then, look,
So stop it.
molecule.
And then do display photograph.
Okay. So this needs
Now
to
make
be
it like.
highlighted. So the other one. And then molecule.
That's just the thing.
Yeah. I should go to try to restart. Is it working for you?
No, I'm having trouble visualizing it. I'm loading it. I think I'm loading it all right, everything, but it's never displaying.
There's no frame. So highlight this.
This is
Move over.
this is the only
Just rotate it.
Oh, so you've already done that. So now you have to load it together. That's the new. Okay. No.
Can't you share your people in the car? It's like, sign.
I got it.
Are the easiest?
I do have a question. That I think it was good. Someone, and they just do it. Yeah, so go to display. So graphics. There you go. Yeah, we hit the equal sign and we'll let it rotate. And it'll rotate it all. And then graphics representation. The drawing method.
It's a coordinates. There it is. It doesn't work.
Yeah, this is like.
Thank you.
But it is, everybody at least have, well, we can show it here. So I want to briefly describe what you're seeing here. Let's slow it down. So we start, like I said, this is just configuration rec staging. And I actually don't know how to create it. You've never told me. And that's one of the reasons that I have to minimize it. I want to make sure that there's no overlaps and doesn't blow up. This afternoon, like I said earlier, if you want to start, when I tell you how to do a production run with this, I tried it, and for me, it just blew apart. So we're gonna, there's algorithms to find the minimum of the potential energy. And yeah, it's too slow. Is it moving? Slowly. All right. And so what it initially does, it's finding a local potential energy minimum for all the particles, for all the molecules here. So you can see that it actually initially kind of spreads apart a little bit. And this is really due to those overlaps. And then then you can see it kind of compresses and becomes a little bit more circular. It's not a global energy minimum. So if there's a crystalline state, you may not find that, it may find it. But it just finds a local potential energy interval. So now let's learn how we tell Amber to do this. That's not what I wanted. And you can play with looking at different structures and stuff. I wrote this before I knew you'd know VMD a little bit. All right. So this benzene.prm top contains information about the force field that identifies the atom. And this minimization program is going to be, the first example I'll show you, a molecular dynamics script. It has the following format. This is an Amber format. The first line is just a comment line. It's good to put something descriptive in there. To say what you're doing. I think mine is not the most descriptive, but put something descriptive in there and something when you go back later and look at it, that you know pretty much what you did. The second line is ampersand control. Then you have lines describing your simulation. First simulation we have is this minimization. But the line, these lines that describe the simulation, lines start with a keyword. A lot of them keyword equals number. I don't know all the commands. The number sometimes is an integer that's just a flag. It's just telling it one of the several options of things that it can do. Or it's a floating point number, which can be a parameter in the simulation. Like the time step. You numerically integrate equations of motion. There's a time step in this numerical integration. So, and there's other numbers. Then there's a comma. Don't forget a comma. In an easy way to have that work. And there are many options. There's somewhere around here, I have the URL for the manual. I'll be the slide. And then there's this finishing line. So let's take a look at the script that just did what. So, the script is here. So this is my first comment line, and being minimization. I actually recommend always putting dates, especially after you do this for many years. You'll be able to get it. The control, I'm in. So over here I'm describing what these things are. There are many options. I'm in here. This is one of the flags for energy minimization. And when the flag is 1, I'm saying perform minimization. NTX is just a flag that you read in coordinates and velocities. Once the coordinates are run in, you don't need any velocities. Energy minimization, you don't need any velocities. For this one, there are minimization routines that actually use velocities. IREST is a flag to run it as a new simulation instead of continuation of one simulation. We'll set this to another value later, but 0 means we're running this as a new simulation. So the energy minimization does 2 things: steepest descent and the conjugate gradient minimization. You don't really need to know exactly what these things are. If you're curious, you can look them up. Or the steepest descent, you have your potential energy. It just finds the steepest way down this multidimensional potential energy path. Times New gradient is a little bit more complicated, where it's where to find the path towards the number. Okay. NTPR, this is every number of steps for that output to files NV out and NV info. I'll tell you how to designate these files next slide. And TWX is the every number of steps the same coordinates. And I put 1,000, I think, for this formalization. The file I actually used is in the folder. I don't even remember how to change this to actually see that. A lot of times when you do energy normalization and get this initial structure, you only care about the last step. And I wanted to show you what was going on, so I put it up on. This cutoff. This is the cutoff for the pair interactions. So right now there's no box. The box is defined a little later, but this is the cutoff for pair interactions. Okay. I out FM. So this is telling you, this is some sort of flag for the format of the output file. There's two ways to save these files. It's a human readable format. And I have all the flags set to the human readable format. This is kind of give you an idea of what's printed out. Human readable formats is just a text file. So it just has positions and velocities. And it has some lines, I'll use some details about what's going on in simulation. There's just some velocities, sometimes like box lengths and stuff, so you know. All right. There's also another flag. I don't remember if it's 1 or 2, but it's in the documentation. That is a binary format. When you do the analysis, you can do it using the binary format. The binary formats are much smaller, much quicker for the computer to deal with. However, if you open up a binary file, all it is a list of symbols. Every now and then you can figure out a word here and there, but just a list of symbols, you can't read it. You have no idea what it is. Most of the time they do simulations for later, not necessarily for this class. But for Martin or someone who is using binary format, it's about 10 times smaller. And consequently, it can actually be over 10 times faster for the computer to deal with it. All right, here's a website for submitting a GPU job, but if you go to the class website, there's a link to it. We're not going to run the memoization right now. If you follow the website, this is the command to run the memoization. I didn't know it created until yesterday. So this is the actual program, PMEMD. That GPU is we'll run it on the graphics card. These run very fast. This is the non-GPU version. And so this is long, this is one line, long line that you have to put in. But once you write one script, it doesn't take a bunch to modify it. But this is what it's saying. So we've done use some links. Dash is the capital O. Is overwrite the files. A little dangerous, but if you can read this out, and then you won't overwrite any output files you had before. It won't run those files. I left it in, but some people want to figure it out. Okay, they have dash I. This is the input script. So this is the script. So we had made a text file, what I showed you on the previous screen, on the left-hand side. This is the script. This script is actually in the examples folder, so you can read it. Okay. And then dash O, this is the log file. And remember, we had the NTPR. So this log file is for every NTPR steps. Right? Dash P. So this is the parameter and topology file. So remember the topology file that you read in the B&B initially? This is the same file. So this is, once again, this is telling now Amber, the same thing as it told B&B, the atoms are, and the parameters for the interactions and everything. We didn't care too much about the parameters and the interactions. I guess it's analysis. Dash C, this is the initial coordinate file. So that first configuration I showed you, this is that initial coordinate file. As our file name, the final restart file, you want to print these out so that you can start the installation. Dash X, this designates the coordinate file. So the MD's coordinates. So this is the standard way to designate the coordinate files for Amber. And then dash int, this is the information file written every NTPR steps. This gives you some information about the simulation, how you troubleshoot work. Okay. So we already did this, loaded it, and checked to see what it looked like. All right. So what do? So after you minimize it, so you can think of a minimized structure as essentially temperature equals 0 structure. But essentially it's a low temperature structure. And so what is very typically done is that then, once again, not to have any problems with the simulation, they heat it from the 0 temperature to a higher temperature. So here's another script where we're going to heat it from 0 temperature to 298K. Probably should be on a new line here. I'll fix that on there. Once again, you have the control, then you have some other ones that we've done. But some new flags here. Now I'm going to have periodic boundary conditions. So we didn't have periodic boundary conditions. Here I've added periodic boundary conditions, cut off the same as before. And now I'm also going to add a flag for the simulation for constrained bonds. It is not uncommon to constrain hydrogen bonds in molecular simulation. Then you it's going to have an idea of why you want to do that. Why? No? Well, the hydrogens can move very fast. If you constrain the hydrogen bonds, you get away with larger time steps. Time step is too big compared to the motion of an individual atom, then you don't, the integration algorithm doesn't work anymore. So, In these simulations, we would be training the hydrogen bonds. And if we do that, we want to not necessarily calculate the forces in these hydrogen bonds, because there's no need to. And so we don't want to waste the time calculating those forces. We're just going to throw out in. I have a flag saying that. So I'm heating it from this initial temperature, temp I, 0, temp 0 to 98. But like I said earlier, Newton's equations of motion doesn't have, when you run Newton's equation of motion, there's no temperature in there. You don't learn physics. There's a T somewhere in Newton's equation of motion. So we apply what we call a thermostat. And there's different thermostats. The NTT is your flag for temperature component here. And I'm going to use what's called a London dynamics thermostat. I'll read this guy what that is in a little bit, but that's the thermostat I'm using. Okay. In my thermostat, which I will tell you about, is a gamma. And that's a parameter for the thermostat. It is important to choose the parameter somewhat wisely, but people know what this parameter, what are good values of this parameter. So this has been studied about that. It's not hard to choose the right parameter. Generally give the documentation program. Okay. We're going to run it for 25,000 simulation steps. Now we need time steps. We have a numerical algorithm that we're going to use. And this is a time step. NTPR. Oh, yes. This is how often we're printing it out. And the London thermostat needs a random number C. It uses random numbers for this temperature component. So IG is the random number C. If you use the same C for a random number generator, it generates the same sequence of random numbers. If you restart it with the same C, your simulation should be the same except for round off errors. Serialization changes that. A -1 parameter means use the date and the time of the random numbers. And what this does is make sure that your seeds are changed. The thermostat and the trajectories will change with each seed. If you want to change the trajectory, you change the seed, and you'll proceed a little bit. So it's typical to use the same time. It's just an easy way to change the seed every time. If you want to recreate the same trajectory, you can run it on one processor, the same seed, and recreate the system. Oh, yes. Yeah, oh, it's ASCII. So the FM families. So here's, once again, how you would run it. It's the same as before. But here you notice that I had a restart file, then a restart for the normalization. So I'm going to start this one. This is -C. C, and we put a line, this is all printed in one line. And this is the restart file. And we have a new restart file, heat. So we start from the minimization and heat it. And there's an example in the examples, so we can take a look at what this looks like. So I'm going to delete this molecule, delete it, load in a new molecule, the same parameter file. The easiest way is when you, after you hit load, just hit browse again, and then it'll be loading it automatically into this one. And then heat. Now you want to be careful if you hit open. And this time you want to load it arrow coordinates with periodic box. Okay. So this is it heating. Oh. I'm going to zoom out. All right, and so here, within saving the coordinates in this simulation, the molecules are going through the periodic box. I'm only showing the molecules within that started in that I initially read it in the initial position. They're going through the periodic box, but because I'm not showing the images, the image molecules, it looks like they're flying off into a vacuum. This isn't what's going on. So let's take a look at what this liquid kind of looks like. And what you can do if you go to graphics, representations, hit periodic, you can add images. So now you can kind of see where the box was. I don't have the Z's because the Z is coming out at you. It just adds difficulty. So this is the end of the minimization. I had the box within the parameter file set up around here. So you notice it's not filling up the box. So then I decided to heat it. We're going to finish this. So we started heating. The molecules are moving around. And you can see all these periodic images. Once again, this one molecule, sorry, this box actually is interacting with the one in the adjacent box. All right. So that shows you heating simulation. So now we've heated it from, that's not what I wanted. Remember, we heated it from 0 to 290, yes?
Is that the reason why they're all reacting the same way? Like it's the same 200 benzene in each box to start with, right?
Yeah, so
So
what I was showing, right, so that we had the initial box, and the ones shown around it are periodic images. So it's really the same molecules.
Right.
And they can interact through the box with another molecule. Yeah, those are just periodic images.
Right.
So what we imagine is that we just tracked the particles, one set of particles that we imagine are within this center box. But they can interact with another molecule in another periodic image of another molecule within the center box, right? Or imagine that that's the infinite system. And historically, it was debated whether or not this would work. People didn't necessarily weren't convinced at the beginning that it would work. I worked with a professor who, when he first started doing this, they actually took used this idea with periodic images, and they did a huge simulation look at the center. What happened in the center? They compare it to convince themselves that it was right. These days, people just think, yeah, of course it works. Yeah.
So I guess on that note, and this might be a longer question for another day, but if we're running these simulations that look at a scope of like nanoseconds or even smaller, and we can't reasonably observe that kind of thing experimentally, how do we know that it works? I mean, I guess I understand that the math makes sense and that like logically.
In what sense do you mean, how do you know it works?
I mean, how do we know that it's accurate to some extent? Because I mean, we're introducing these artificial restrictions on hydrogen bonds, and we're doing these tricky things of periodic boundary conditions and everything.
It's a good question. I mean, and to answer some of it, first of all, the periodic boundary conditions can and do create artificial effects. One of the most notable ones is with the, and they didn't talk about force fields, with the electrostatic interactions. These are what is called long-range forces, the long-range interactions. And sort of these long-range interactions, and you can kind of imagine why it could be a problem. Because you have this small cell, you have to deal with these long-range interactions and how these particles are interacting with image particles, and then itself. Because if you can't truncate it short enough without making some sort of artificial effect, you have to deal with self-interactions, you have to deal with those sort of correlations. So that there are actually well-known issues with that. To answer whether or not it works is, one is you have to think about the question you're asking. Are these problems, like the problems of the long-range interactions, going to make a difference for those questions? The other thing with the periodic boundary condition, you can a lot of times get away with it for simple liquids, benzene, things at high temperatures, because there's no long-range positional correlations. A particle that moves over here, its energy kind of gets dissipated into the surroundings, or it affects the motion of the particle over here. This is also not always the case. And those can be very hard to figure out whether or not that's making a difference. So what is typically done, and I studied supercooled liquid and glasses, and I have to do this all the time, is do a simulation. Like I said, a lot of times I do 1,000 particles. I get results, and then I go, well, okay, are these right? So to check it, I double the box size. Right? And then I do the simulation again. I get the results, and see if they agree within the error. Within error, we generally go, all right, that must have been big enough. Once again, that's not actually always the case, but that's the typical way to do it. So if you are concerned about those sort of problems, the ways that is, is my simulation big enough? Make it bigger. Sometimes you don't have time to do that. So you go into the literature, what other people want to say is big enough.
That's generally understood, kind of where the boundaries of molecular dynamics can approximate things.
That is still being explored, I would say. But yeah. The other problems you run into are the force fields. I showed you the Leonard-Jones interaction. The R to the 12 propulsion and R to the 6 for the traction force. R to the 6 has a theoretical backing. The 12 is a numerical convenience. These things are not, if you do the electron instruction calculations, the quantum mechanical calculations, this is not what force fields would look like. But it doesn't seem to make a huge difference. And again, it depends on what your questions you're asking. My questions I ask is basic theory. Is this theory able to predict the motion of a liquid? So now, not dealing with real systems. That's easier to deal with. If you're looking at proteins, then the force fields may make a big difference in how you deal with these interactions. These are questions that you have to worry about. Martin worries about that a lot. And he'll be a good guy to talk to about it. He's very good with it. All right. So that's a typical second step is heating it. This is how we run it again. All right. So after you've heated it, you notice that after we finished heating, that didn't look like a very uniform liquid. There's huge gaps, huge holes. It's not equilibrated yet. The next step, you have to equilibrate the simulation so that it acts like a liquid at those conditions. So, since for this, we're going to be interested in what's typically called ambient conditions, from room temperature, 290 K, 1 atmospheric pressure. And you change these relative to what questions you're asking. But, so this is a typical equilibration script. I did not put my initial line up here, a comment line. And control, and then these have been over, there were simulations, the time step, over. Then a number C. All right, and we're going to do a constant pressure simulation. And this is isotropic pressure scale. So how do simulations deal with pressure, change pressure? So what a simulation will do is there's statistical mechanical theories for how to calculate pressure in your fluid. So it calculates the pressure. And then it changes the box size, depending on if the pressure is too big or too small. Sometimes it's somewhat random where it's more likely to go one direction or the other, but it's still random. So if the pressure is too high, well, what should it do? It should make the box bigger. That decreases the pressure. If pressure is too low, it's going to make it small. All right? So for simple liquids, your pressure is going to be uniform, the same in all directions. At least an average. The pressure is. And so what this is set up to do isotropic pressure scale. So that means when it changes the box length in one direction, it'll change it in all the directions the same. If you're studying films, if you're studying something that systems that are not themselves isotropic, like fluids, then you may want to change that parameter so it scales the pressure differently in different directions. Not isotropic pressure. Yeah, it changes the box length. That's all. That's pressure. It changes the box length differently in different directions. All right. So this is set up for isotropic pressure scaling. Okay, the barostat. There's different ways, once again, to change this pressure. Just like double the temperature, there's different ways to change the oxide and pressure. What you want it to be, this one uses what's called Monte Carlo algorithm. And this is there. Okay, this is the pressure that you want it to be at. And so units are atmospheres, so you want to go atmosphere. Going through these, cut off again, outputs in the text file. Okay, IRAP, 0, I think this is the default. Do not be putting the particles back in the box. You can tell it every timestamp to always translate the particles back in the box. Then, if a particle were to leave this box, and you look at the movie, you would see it instead of going out over here, it would just automatically appear over there. That's wrapping it back in the box. For, in my opinion, you essentially never translate the particles back into the box unless you're starting a whole new set of simulations. And I'll show you why, because it's really easy to do this. Wherever the particles are, it's really easy to put them back in the box to calculate things if you want to do that. However, when you calculate time correlation functions, we're going to talk about, it's really hard to determine how often the particle leaves the box. So if you want to, when this particle leaves the box, and you want to calculate its displacement, you don't want to calculate the distance between here and here. This displacement is displayed over here. So you want to track the particle that's going over here, and you want to calculate this displacement at this distance. So every time, if you keep wrapping them into the box, you have to then, to calculate displacement, figure out how many times it leaves the box, and in which image it could be in. It could be in the limited way over here. At a later time. That's funny. All right, equilibration. So this is similar to what was before. There's a program, and this is the thing that I'm not too sure it's going to work, so I'm going to define it for you. So you can look at these two log files. And then I've run this file process and the out and this should be in your path. Check that running today. And then the this is the log file for the run that you want to look at. And you go to equilibrium, you run a log file, and then it writes out all these summary files, just a whole bunch of summary files. So this is kinetic energy total and temperature. Okay, these two are very similar because it's calculating the temperature in total kinetic energy. It's related to, this is how it does it. So 1/2 the average, average of sum over n and then the n squared. Average kinetic energy. So for the zero zone, this is 3/2 and is right? So for each time step, and it's putting out kinetic energy, which is this whole kinetic energy, which is this sum. It calculates the temperature for that time step. And so these two are related, and that's why this factor. I always emphasize this because this is not the only method to determining temperature. This is by far the most common way of doing it. So I'm going to quickly show you there should be a Python script in there that will what's that going to work here? Where was I? Here. And there we go. So if I go to calibration, there's two columns. So this is showing, yes, so this is the time, the simulation, and this is the kinetic energy. What the thermostat is actually doing is fixing this kinetic energy sometimes. Not fixing it to one value, but it's having it fluctuate around the proper value for the temperature. So that's how it's equilibrating it to that temperature. So, I don't remember that. But if we look at the potential energy, right? So, so this is just the potential energy. Remember, you have these force fields defined through these potentials. All these time steps is calculating the potential energy. And potential energy is decreasing. When this thing equilibrates, the potential energy looks like what you saw the kinetic energy look like. It stays, fluctuates around an average value. And that's one way to determine initially that you're in equilibrium. This simulation did not equilibrate. So this afternoon, you're going to equilibrate the simulation. All right, and also, this is what it's doing with the volume. So my box is too big for the pressure I wanted. And so at that pressure, the density is actually larger than what I had initially defined. So what it is doing in this modifier algorithm is shrinking the box as if I put it. Once again, when this equilibrates, this is going to fluctuate around some sort of average value. And you have to wait for that for the equilibration. So this afternoon, you'll be equilibrating it. It shouldn't take too long on a GPU. It took me 2 hours on the CPU, one CPU on an old computer. So the GPU is probably 10 times faster. So it shouldn't take too long. Didn't have a chance in France to try it on the GPU. All right, so back to. All right. So these are two things we need for equilibration. So after the class, you have all those files. You can use the end of the equilibration file, restart. Create an import file, run some information, and save trajectory, output information every 100 time steps. And this is I ran it for 1.5 million time steps, and then equilibrate. So you guys really deserve to know, at least as an idea of kind of what we're doing. So I told you we're using monument stuff. Well, that is a modified Newton's equation of motion a little bit. The modifications, so this is second time derivative. What is second time derivative? Acceleration. Okay. This is the first time derivative, or dot. These are the velocities. If you imagine this, think about it. We've got differential equations, but what the equation without the force and the random force, this is the equation for exponential decay. So what this gamma does is it's essentially a friction. So as something moving at a certain velocity is slowing down. This is what we call friction. This is what's put into a gamma ln. This is what's put into the number square. Right? This is the forces, so this is the forces on the motions. This is the same thing. Mechanical potential, same forces of the floor. This RT, well, if I only have the friction, so everything I have that's slowing down, I have force. Well, it just eventually stops. So what I need to do is give it kicks. Right? So what I do is I give it these kicks. So this RFT is related to the gamma. So it's got kicks such that it simulates these benzene molecules put into some sort of solid of really small particles at the specified temperature. And this is, in a sense, an imaginary solid. This is how this came up. It's Brownian motion and how they came up with the idea. And so this simulates these benzene molecules being surrounded by a heat bath. So that equilibrates it at the specified temperature. So 4 choices will first like gamma will equilibrate the system slowly. You can read the choice I had, a decent choice. You can read the Amber manual to find better choices too.
I have a quick question about that slide.
Yeah.
So the RFT is essentially an approximation for the kinetic energy supplied by your solvent.
I'm not going to say no. I mean, that's so if you think of a big molecule in a solvent, right? There's one is not too big. I mean, there are 2 things going on. One is that the solvent hits it, right? And that essentially is the RFT.
Yeah.
And then gamma is a solvent when it actually hits it, slows it down.
And that's somebody.
That's the gamma. There's a relationship between these two to get you the temperature. Okay? So, I couldn't find Amber's specific bar set. So this is how these work in general. So every now and then, it's going to try to change volume by a certain amount. And then it can calculate the pressure. And it rejects these volume changes according to the Boltzmann distribution, to proper thermodynamic gas solvent, so that its pressure is sampled correctly. So that's what the varostat does. So after you do an equilibrium run, yes.
The varostat is like making the volume smaller. So in a sense, like it make that grid like it's very given size, right? Make the volume smaller.
So the Monte Carlo So in our example I'm running, right, in the benzene example, the box I chose for one atmosphere was too big. So that's why it's shrinking.
So then, would that affect like the kinetic energy? Like if it's like going towards the wall and then it shrinks as it's like as the benzene moves in that direction?
But there's no physical wall. Remember we have periodic boundary conditions.
Oh, so once it goes.
So yeah, it can still go through the wall.
Okay.
So when it shrinks the box, what it does is it moves all the particles by that specified amount. Right? So if you were to shrink the box by this amount all the way around, takes all these particles and moves it, you know, and so it isotropically, so it basically just moves all the particles together such that the does that make sense? I don't know if I'm describing it that well. But yeah, it just moves all the particles together. Then it can recalculate the pressure because the particles all got closer together, the forces have changed.
But they're all moved proportional.
They all move the same amount. Yes.
Okay.
Yes. So when it expanded, they all move the same amount too. So that's the isotropic one. You can do it with just two sides, where you just move these sides out. These particles just move apart in one direction, together in one direction. So that'd be a non-isotropic. And also other ones too, where they change the shape of the box. But there's many different ways to do it. All right. So the production runs, this is what I was saying, you want to design these to produce configurations for your desired calculations. Sometimes, I think, talked about thermodynamic ensembles yesterday a little bit. Sometimes the desired configurations are not what Newton's equation of motion produces. In my example, we're just going to numerically solve Newton's equation of motion. One of the issues that people, especially in the bio world, run into, that computers aren't perfect, run really long simulations. Newton's equation of motion technique conserves energy, but energy will slowly drift due to numerical issues in various times. So there's different ways to kind of deal with this. Some people rescale the velocities, get rid of it, and do different things. But this is an issue to always keep in the back of your mind. So carefully chosen constant temperature simulations, the logical thermostats, not the best one, but there are other ways to do it that can stop energy drift. But you also need to be careful to know what's going on there. But when you start doing your projects, be sure to discuss with everyone exactly what sort of calculation you're doing and what positions you want for your particles. Does it need to be a Boltzmann distribution of positions? What are you looking at? So when we're done with the production runs, what we do is we use positions and velocities to calculate temperatures of interest. Most of the time, it's just positions. A lot of times, people throw out velocities. It's space, they don't even. Should have made those P's. All right, but so P stands for momentum. This is all the positions of the particles, all the momentum of the particles. Momentum is related to the velocity. So when you take a simple average, these brackets correspond to averages, thermodynamic averages. You say so many configurations, two configurations right next to each other are nearly identical. They're going to give you similar values. You need a run that's long enough so that you have enough configurations to get a good average. So you say, so do the average, just sum of whatever you're calculating, over the number of configurations. This is the same as saying that take the sum of an integral, and your integral integrated out to infinity. As long as you have enough position saved, you save enough configurations. These two will be equal, and that's a simple thermodynamic average. Two things we typically calculate are static correlation functions and time correlation functions. So, for a static correlation function, we call it equal time correlation function, but you have two functions. I'll show you some example later, but we can take the thermodynamic average of this. All this means is that you're doing this procedure with two functions multiplied together. It's very essentially the same. I'm going to this. So it's the integral at the same time. There's time correlation functions. These are a little different because you have now the time origin, and now you're interested in what has happened here. So you integrate the average, the integral for the time origins of one function times the other function evaluated at the later time. Right? All right. This is all math, and probably like you, I don't find it that illuminating until I see examples. One of the most common static correlation functions in liquids, if you do simulation with liquids, you will be calculating this. So we will do a calculation of it. It's a pair correlation function. This stems from really a product of two delta functions. So what this pair correlation function is, if you imagine your molecule and sitting at the center of a molecule and thinking of a little disk around it, delta function means the disk is infinitely small, but you can't really do that on calculation. So think about a little disk around a molecule. We're counting the number of other molecules whose center their molecule is in that disk. Right? And then we're dividing it by the density. Now, what is the division of density? Division of the density makes this, so if everything's uniformly distributed, what you get is that G of R will equal 1. The division of the density, this makes this go to 1 as the large distances are. So this is, here these bold letters mean vectors. Here, these are still vectors, so this is the distance between two molecules, two atoms, 2 points of some sort that you're defining. This is part of this, I think. So, all right. Delta's direct delta function, which I hate to call a function, it's really a probability distribution. These are typically used to characterize the structure of your liquid. So, this is how you actually calculate it. So, like I said, you divide the intervals, radial intervals between a minimum and a max, and step sizes of your delta R, some sort of distance. And then you find the distance between each pair of points, which could be your atoms. Could be, I'm going to have you do the center of the benzene, the geometric center of the benzene. So it can be center of mass. I didn't want to deal with having to divide by masses all the time. So geometric setting. So you create a histogram. You guys talk about histograms yesterday? Okay. You just create a histogram of the points where I is the integer, the distance between the molecules divided by the size of your disk of I. And you do this for you say configurations. Okay. And you take your histogram divided by 4 pi r squared. Wow. Big delta and small delta are the same thing, right? And the number of configurations. All right? It should be that. All right, I'm going to update this. Put it back on the Dropbox. Right, in the folder. It should be divided by density. All right. So, one of the things that people calculate this is say you want to know the number of atoms or molecules around a specific atom. So this interval, 4 pi rho, and you are delta r from 0 to r. So this is, you want to know the number of points from center of the molecule copy certain distance. Then you can pull that into the number of points or molecules. So, like I said, we have periodic boundary conditions though. So, say you position a molecule from here, way over here. However, you want to calculate the distance between the molecules within the box. So how are we going to do this? There is a simple way to do it. What you do is find the distance between x, y, and z positions. Right? And for example, the x separation between any two particles is given by the length of the simulation box in the x direction. And the nearest integer is the nearest integer function of that distance divided by another. You do that for the y and z directions also. And then you can find the distance, which is the square of the distance is delta x squared plus delta y squared plus z squared. In Python, you can write the nearest integer convention, integer around your number. So you do bounding delta x squared y delta. Right? All right. So here are examples of time correlation functions. Two of them that are actually related are velocity correlation, color correlation function. Once again, I'm taking thermodynamic average, and this is the sum of the number of particles, the velocity times 0, times the velocity times t. Right? I'm dividing it by the number of particles, thermodynamic average, divided by the number of initial condition that mean square displacement. So this is similar, where I'm now looking at the displacement of a single particle. So this is always a single particle, not square. Another one down here is the energy correlation function. This is another time correlation function. But you notice that these, we call these self-averaging because they, this is single particle quantities. This energy correlation function would be time correlation function of the whole system. functions like this can be used. One is after you equilibrate the simulation, you get an idea of how long it takes for it to forget about its position, set position. When this decays to about 0, it's kind of forgotten its initial energy. These are because it depends on the global quantity. Here, for every particle, you have essentially a correlation function. So for 200 benzene molecules, like and the centers, it means for the space, the benzene center, you get an average over 200 molecules. Here, we're just averaging over. So self-averaging ones generally converge faster. All right. So I'm going to have you calculate the mean squared displacement. And it's done very similar. This is not, looks long, but it's not too scary. This is just X, Y, and Z directions. They're independent, so you can calculate these separately if you want. This is the sum for the number of particles. So this is the displacement in the X direction. You take position particle times 0, and time equals t, square that distance, sum over the number of particles, sum over the number of time origins, you say time equals 0, and you divide by how many origins you have. Let's see. So here's an example of what the mean square displacement looks at large times. In a liquid, a long time, the mean square displacement is calculated. This is the diffusive motion of the particles. We can find diffusion coefficient. It gives you an idea of how fast the particles are moving through the liquid. The molecule are moving through the liquid. And this diffusion coefficient is related to the mean square displacement or the velocity relation function. And this is an example of what it looks like in the centers of the benzene molecules. So now we have a trajectory. We kind of know what we want to calculate. We're going to calculate mean square displacement, diffusion coefficient, pair correlation functions. We now need to learn how we're going to do this calculation. So this MD analysis toolkit is a Python tool that lets you read, write, and analyze molecular dynamics trajectories. Oh, it should be once. So when you start off with your Python script, you want to import MD analysis and NumPy. So I generally import it as NP, like if I write typing. Import math and SciPy also useful. The first thing for MD analysis is you create a universe. And this universe is created by MD analysis.universe. And there's a topology file. And this topology file is the PRM top file. So the first file that you write into PNP, file. And you write in your trajectory file. So this is the same file you write in PNP for visualizing. Then you make a selection of atoms. So the selection, well, you typically select atoms. And so this is how you can make the selection of atoms. There's many different, you'll have to look at the online documentation. There's many different ways to make atom selections. Because after you read in the topology file, it will define many different ways to do it. And a lot of them mirror VMD's atom selection command. So you can select atoms by indexes, IDs, types, all the carbon atoms, that kind of stuff. Atoms a certain distance away from something else. All right. So remember, to do all those analysis, I need to loop through the trajectory. I need to at least get those time points. So to loop through a trajectory, so this is for TS, stands for time step in my universe, that trajectory. I get the coordinates, and this is a numpy array. Okay, you get that. It's the TS, whatever I define here, positions. I get the dimensions of my simulation box. The box, once again, is TS times dimensions. And so if I want the position of a particle I, so if I have a simulation with 2,400 particles, it goes from I goes from 0 to 2,399. And those particles is defined in the parameter file. And then J here is the position. So for particle 0, the x position of particle 0 is coordinate 0, 0. The y position of particle 100 is coordinate 99. All right. Box is just 3 numbers. The box J is the length of the simulation box, the J direction. And we can run the calculations and print the results. For this class, this is the first time I've ever used this, so I had to learn it myself. And so to learn it, what I did was I took the first benzene molecule, printed out its center, the center of the benzene molecule, as it moved through my simulation model. Just so I could learn what was going on. So once again, I took the universe, I selected the atoms, selected all the atoms, pretty easy. Printed out the number of the atoms in the selection, just to make sure that it was what I thought it was. The length of the trajectory, see how many frames was in the trajectory, make sure I understood what was going on. Open the test file. So for every time step in my trajectory, I have my coordinates, boxes, and then I define the center, the x direction, y direction, z direction. So for every I in range 12, why am I doing this? There are 12. Yeah, so this is just the first particle, right? So there are 12 atoms in my benzene molecule. So center of the x direction equals the center of x plus the right atom x direction. Y is right atom y z. Right? And then now it's 12 of them, so I have 5 by 12. I printed it on the test file, and you can plot this and see its trajectory. So that's just an example script, how to do it. And with only 10 minutes to go, so for this afternoon, I'd like you to minimize and equilibrate the benzene simulation. You have the examples that have normalization, the heating, and the initial equilibration. Okay? Then on the constant energy production line, 300,000 steps. So there's the amber So, in the error guide, they'll tell you how to do the calculating. This is just solving unit equation. And so then I want to compute the pair correlation function for the geometric center of the benzene molecule. The script I showed you before was how to get the geometric center for the first benzene molecule kind of print out its trajectory. So you want to do this for all benzene molecules and compute the pair correlation function. And also compute the v-squared displacement for the geometric center of the benzene molecules and get the diffusion coefficient for the benzene molecule. The diffusion coefficient, once again, is a slide earlier that shows you, but it's related to the long time limit of the mean square displacement. Here. All right. If I remember right, this is actually what the mean square displacement should look like.
It's a little wiggle at the top.
It's statistical error. Yeah. So think about it. When I do this calculation, my simulation is this long. I have this many time steps to calculate. When I calculate this time, I calculate this time. I turn it up. So the statistic at the later time. Okay? All right. All right, so that's essentially it. That's my office number again. Let me find the let's see.